Okay, so let us start with the final problem of recitation 3, that is question number 5. So over here we have to model a person doing push-ups as a 4-bar linkage. So on the right hand side over here we already have a model of 4-bar for a person doing push-ups. So we have to solve the vector loop equation for this problem as well. But before going further, let me identify the unknowns. So let us make a vector loop first of all. Here it is R1, R2, this is R3, and this one over here is R4. Value of R1 here is 52, value of R2 12, value of R3 14, and R4 is 57.7. Theta 1, that is angle of the ground link with horizontal 0, theta 2, which is given as 45 degrees, theta 3, which is unknown, and theta 4 is also unknown. So this is quite obvious that we have two unknowns and we'll have two equations from the vector loop. So now I can write the vector loop equation, which will be equal to R1 plus R4 is equal to, so location of RC is equal to R1 plus R4 is equal to R2 plus R3. Now I have unknown theta 3 and theta 4. Uh, so what we can do is uh, we can bring R2 on the left hand side. So R3 finally it will look like as R1 plus R4 minus R2. Now if we write with x coordinate, then it's R3 cos theta 3, R1 cos theta 1 plus R4 cos theta 4 minus R2 cos theta 2. We know that theta 1 is 0. So this will turn out as R1 plus R4 cos theta 4 minus R2 cos theta 2. For y, it is R3 sin theta 3, R1 sin theta 1 plus R4 sin theta 4 minus R2 sin theta 2. This is 0, so this whole will turn out as 0. So equation will look like as R4 sin theta 4 minus R2 sin theta 2. So here is first equation and this is my second equation. So to eliminate theta 3, what we can do is square first, square second, and add both of them. So if I do that, my final equation would turn out to be as this one, a cos theta 4. As you know, I have already eliminated theta 3, so my equation will be, so variable of my equation will be theta 4, and that will be b sine theta 4 plus c. I am skipping some of the steps, but I would recommend you to go through all of them. Value of a will be 2r4, r1 minus r2 cos theta 2. B will be minus 2r4 r2 sin theta 2. And C is r1 minus r2 cos theta 2 square plus r2 square sin square theta 2 plus r4 square minus r3 square. If I evaluate, and you know you can find the parameter from here, r1, r2, r3, r4, and theta 1 and theta 2. So these are the 6 parameters that we already know. And if you substitute value of those parameters over here, A will be this, B will be minus 979.2, and C will be 5098.8. As we did earlier, what we need to do is we need to convert this equation into half angle of 10. So tan of theta 4 by 2 is equal to t, and cos theta 4 will be 1 minus t square upon 1 plus t square. Sin theta 4 will be 2t upon 1 plus t square. And if I substitute value of this and this in the equation, which is this one, I will get the final equation as c minus a into t square plus 2bt plus c plus a, that is equal to 0. And you already know how to solve this equation. That will be t is equal to minus beta b plus beta b square minus c square plus a square upon c minus a. And value of beta will be plus 1 and minus 1. So if I solve this equation with plus 1 and minus 1, I will get t1 as 18.142, t2 as 7.226. So this will give me value of tan theta. So it gives value of theta 4 as 176.99. In this case, value of theta 4 will come out as 164.242. So we need to check which one is correct. So let me make a very basic diagram, and that will be easy to understand from that. This is first revolute joint, second this. So this angle is fixed, and one of the solution I think can go like this. And let me change my color. So one of the solution can go like this, and other one can go like this. So this one will be smaller angle, 164 almost. And this one over here, this is bigger angle, that is almost 176. So we can say that angle, which is 164, that is correct, because this situation you can see over here is not feasible when someone is doing push-ups. So not possible. So theta 4 is 164.242. And once I get this, I can go back and I can get this two equations, that those are for first and second. So my equations are, I will write them down again. R1 plus R4 cos theta 4 minus R2 cos theta 2 is equal to R3 cos theta 3. So if I put value of theta 4 and remaining parameters in this equation, I will get cos theta 3 as minus 0.8583, and I have second equation, that is R4 sin theta 4 minus R2 sin theta 2 is equal to R3 sin theta 3. Remember, this equation came from x component of vector loop, and this came from y component of vector loop. And if I solve this equation, I'll get sin theta 3 as 0.5132. Now you know what we can do. We can go to MATLAB and do 8 and 2 into the d is for degrees, and we can put 0.5132 comma minus 0.8583, and you will get the answer as 149.12. You can clearly tell that x is negative, so this is in second quadrant somewhere over here. Now the next step is to figure out if it is Grashof or non-Grashof linkage. So S smallest is 12, largest is 57.7, P is equal to 54, Q is equal to 40. So that will make us S plus L, P plus Q. So S plus S is 54 plus So this will be 68 and over here we have 69.9. So this is bigger. So this is non-Grashof type, non-Grashof linkage. Now we have been, now we have to find the maximum value of theta 4. So I have a way through which I can explain that. So let us analyze a situation. I prefer the color. Let me make this. And this is my one bar, and this is my other grounding. And this will be the radius of, so let me see. So I'm just going to, I'm right now just tracing a path for longest link, that is 57.7, and this was 54. So this is the path through which my longest link can travel on this path. So let's assume for one example my link solution is looking like this. So you can clearly understand from this diagram. In other case will be, let me change the color, and the other case will look like as this. Yeah, I know the lens are not correct, but it will be something like this. So you can clearly tell that maximum will come when this is fully extended like this. This is this. So in this case, L second link and third link, that is R2 and R3 are collinear. And now we want to go, and I can claim that this is my maximum angle. I can claim, oh, sorry. So I can claim that this theta 4 from the, no, I was right. We have to maximize, we have to maximize this angle. So we can say that this angle give out the theta will be maximum when my linked R2 and R3 as a line. You might think that if we can, if it is it a way that we can, uh, is there a possibility that we can go somewhere over this? But I would say no, because circle for this one is going somewhere like this. So this is when, so this is the trajectory that will be followed by this point. If I look it from the perspective of this link combined R2 and R3. So from this point, R3 is going to go down and not up. So we can say that this is the maximum possible angle that link 4 can achieve from the ground. This theta 4, theta. Now, if I have to write the maximum angle, then it will be, so this angle cos of theta will be cos inverse R2 plus R3 whole square, sorry, that will be 54 square plus 57.7. Let me correct myself. This is 52 and this is 52 square and minus 14 plus 12 square upon 2 into 52 into 57.7. And if you solve this equation, the answer that you would get is 26.78 degrees. Now let us analyze this case in SolidWorks. So as I was explaining, here is link R2, R3, R4, and you can check the dimension as well. So this was the second case which we were discussing. So if I tell you to measure the angle, evaluate and measure, select these two lines, and you can see this angle is almost 173, and that was the other solution. That wasn't that was close enough to the other solution. So you can clearly see that this is what we find out, that the smallest angle will be the solution. So smallest was 164, and that is our solution. So that's how you can visualize this in SolidWorks.